All right, let's get started here. So my name is Guy Bressler. I'm in the EECS department at MIT, and it's a great pleasure to introduce my colleague, Ankur Moitra. He's in the math department. He's a mathematician and computer scientist studying the algorithmic foundations of machine learning. Ankur is one of those rare individuals that you can talk to about anything, any portion of your research, whether it has connections to probability, complexity theory, complex analysis, number theory. It doesn't matter. He'll be, one, interested to speak with you and curious about it, and two, will more often than not have a really insightful suggestion that actually goes somewhere. So it's super rare. He's over and over again made pioneering contributions solving central problems in theoretical machine learning. He often brings a very fresh perspective to long-standing problems for which the field has kind of largely just completely given up on or not even realized that something might be possible. He's been recognized by numerous awards. I won't take up any of his time or your time by listing them, but there's a bunch of them that you can go find on his website. Today he's going to tell us about sort of recent progress on a fundamental and important central problem that one way or another every single one of us has come across, either on the way to this meeting or more directly in research. So with that, I'll invite Ankur to the stage.
All right, good morning, everyone. Hopefully you can hear me okay. All right. So thanks for coming. I'm going to be talking about learning from dynamics, and this is based on joint work with Ainesh Bakshi, Alan Liu, and Morris Yao. So my goal in the talk today is to tell you about one of the central problems in control theory that really goes back to the founding of the field. It's the problem of learning a linear dynamical system from data. Now, despite the fact that it's been studied for over 50 years, as I'll explain, there are actually some shockingly wide gaps in our understanding of what's possible. So my goal today is to give you a simple, practical algorithm that's going to fill in these gaps. All right, so first what I want to do is I want to explain what a linear dynamical system is. Now, it's really defined by two governing equations. These equations are going to come up all throughout the talk, so let me go through them slowly. You should think about a linear dynamical system as being one of the canonical models for time series data. And what's happening is that you have a hidden state, xt, that's an n-dimensional vector that's evolving over time. Now, the crucial thing about a linear dynamical system is that you don't see the hidden state. It's hidden. Instead, what you observe are the input-output behaviors of the system. So at every time step, there's an input control vector, ut, and there's an output observation vector, yt. And these can have different dimensions. Now, each of the matrices that show up in these two defining equations have special names and special roles. The most important of which is the A matrix, which is called the transition matrix. That describes how the underlying system would evolve on its own in the absence of control and in the absence of noise. So it's going to tell us a lot of the steady state properties of the underlying system will be controlled within the spectra of the transition matrix. Equally important are the matrices B, which is the control matrix, that describes the relationships between the inputs to the system and how it affects the hidden state. And finally, we have these C and D matrices that describe the relationship between our observations, the yt's, and how they depend on the hidden state and the control. Now, last but not least, this entire process is not deterministic, it's stochastic. So there's some element of noise, both in how the underlying state evolves, that's called the process noise, and there's also noise in our observations, that's called the observation noise. Now, for the purpose of this talk, you can think about the noise as being Gaussian random vectors, but as you'll see, everything I'll tell you will generalize much beyond that, as long as you have a finite number of moments for the noise. So this is what a linear dynamical system is, but maybe now is a good time to take a step back and explain why they're so important and fundamental. So they've been studied for 50+ years. In fact, some of the most celebrated applications of them are in areas like robotics, navigation, and tracking. In fact, they were literally used in the moon landing, and they won the National Medal of Science in 2008 for their role in the moon landing. So here, the way to think about it is that you have an object, in this case, the space shuttle, which is on a path from the Earth to the moon. And what you'd like to do is you'd like to track the position and velocity of this object. The trouble is that you don't directly know it. Instead, you can only measure it. So at each time step, you get very noisy measurements of the underlying trajectory. You can see that those orange circles are very far off from the actual trajectory. And what you'd like to do is you'd like to use your prior knowledge about how physics works to try and use these estimates to find a smoother estimate for the unknown trajectory. But if you think about it, what's going on is you really have a linear dynamical system. So your hidden state encodes the position, velocity, and acceleration of your spacecraft. And the transition matrix A is just a representation of the laws of motion. It describes the way that velocity changes the position and the way that acceleration changes the velocity. So it's an upper triangular matrix with ones along the diagonal. And in turn, when you have a linear dynamical system, you can study things like the inference problem of how well you can estimate the hidden trajectory when you know the parameters of your LDS. That's exactly what Kalman filtering does. Now, there are other applications which arise in more natural settings, where maybe I don't know what the underlying dynamics are, and I want to try and reason and learn about what those dynamics are. This arises, for example, in natural processes in biology and epidemiology. In fact, there's one particular epidemiological process that's been on all of our minds for the last couple of years, which is the problem of how COVID spreads. Now, you can think about some of the simplest models for how COVID spreads, what's called the SEIR model, are just examples in action of the same type of paradigm, where what you're doing is you're taking the population and stratifying it into 4 different groups, whether the person is susceptible to infection, whether they've already been exposed, whether they're currently infected, and whether they've recovered. And your hidden state just describes how many members of the population are in each of these 4 groups. And your transition matrix A describes the transitions in a state machine. What's the probability that someone who's susceptible ends up becoming exposed, and so on. In fact, what I'm plotting right here is from a recent study where they do a higher dimensional variant of this, where they do an SEIR model that's stratified based on the age group. So they have a different underlying system and transition dynamics depending on which age group you fit into, and then you find even more accurate fits to real-world spread of disease. Let me give you one more example to explain why LDSs are so powerful. This one is a neat one which I learned about a couple months ago, and it comes from medicine. So you can think about in clinical applications, maybe I have some drug that I'd like to understand what its efficacy is. Now in medicine, the gold standard for the way you figure out how effective the drug is you do a randomized control trial. You take a large cohort of patients, you randomly split them up into 2 groups, the treatment group and the control group, and to one you give the actual drug and to the other you give a placebo. And then you measure the outcome, the health impact on each of these 2 groups, and use that to infer what's the efficacy of your drug. Now that's great when you can compose a randomized control trial, but there are many applications in medicine where it's just infeasible to create a very large cohort of patients because you can't find that many people with this rare condition. Or maybe you want to understand what the effect of a drug is on a personalized basis. Things like pain medication, the effect that they have on a person is a very subtle person-to-person effect. And it turns out that even when you have just a single person, there's still something you can do as long as you exploit dynamics. Which is what you can do is you can take one person, it's called an N of 1 trial, and then each week you randomly choose whether or not you're going to give them the actual pain drug or a placebo, and you measure the time response of their symptoms, and by trying to infer the underlying linear dynamical system from that response, you can glean important information about the efficacy of this drug. So this is by no means a comprehensive set of applications. There are also applications in areas like speech processing, econometrics, and finance. But let's take a step back and think about the mathematical model. So remember, we care about LDSs. They're described by these 2 simple governing equations. And what makes them powerful as a model is really, one thing, which is that when the parameters of your LDS are known, so when I know the A matrix, the B matrix, the C matrix, and the D matrix, then I can study the inference problem of given the sequence of inputs and outputs, can I estimate my hidden state? It turns out that that inference problem is very easy and is tractable. That's what Kalman filtering was doing in the space shuttle landing. But what I'm interested in this talk is really the question that comes before that. As we've seen, there are other examples where maybe I don't know from prior knowledge what the underlying transition matrix is. So what happens when I don't know these matrices A, B, C, and D? Is there a possibility of learning them automatically from the data I'm given? Even better, can I do it from just one single trajectory? So this is one of the most basic and fundamental questions in control theory. I'll explain some of the history of this problem, and then I'll explain one particular glaring gap which was sticking out like a sore thumb in the literature, and I'll try and convince you that this is a conceptual problem. All right, so what I'm going to do over the next few slides is I want to formally define my problem, because you have to be very careful in learning theory about setting up the problem in the right way to make it make sense. So let me do it in stages. The first thing I'm going to do is I'm going to define it informally so that we have a rough idea of where I'm going. What I want to do is I want to learn the underlying parameters of my LDS, which are the A, B, C, and D matrices that I don't know. And I want to do that just given one single very long trajectory. And what I mean by that is I'm going to see the sequence of inputs and outputs, the sequence of U vectors and the sequence of Y vectors. And I want to use that information as a way to try and form the basis for my estimator. Now, I should also take a pause and mention that, this is the standard nomenclature in control theory. The U's are called control vectors. Actually, that's a bit of a misnomer because I'm not going to assume I'm allowed to choose the U's. I'm just going to assume that they're passively set for me by a Gaussian or some other distribution. So you should really think of these as being disturbances applied to your LDS, but you'll see that more when I get into the technical meat. But there's one important question I need to address in order to make this problem precise, which is, I'm trying to estimate the unknown parameters A, B, C, and D. But when I have estimates A hat, B hat, C hat, and D hat, how exactly do I measure the closeness between my estimates and the true parameters? We have to choose the right parameter distance in order for this problem to be possible in the first place, and really to capture the real heart of the problem. So let me do that in one slide. So there's a critical definition, which is I'm going to set up the strongest possible variant of the learning goal. What I'm going to want is I'm going to want to find a set of parameters, A hat, B hat, C hat, and D hat, that define a completely equivalent linear dynamical system. What this means is that those two systems, there's no way to tell them apart, even if you have some adaptive strategy of how to choose the inputs depending on the past. Now, for our purposes, I'm just going to assert this proposition. I'm not going to prove it, but this will be the starting point for the formal description of our problem. It turns out that in the context of LDSs, well, two sets of parameters, the A, B, C, D, and A hat, B hat, C hat, and D hat, turn out to be equivalent in this sense of this definition that I gave you if there's a linear transformation U so that their parameters are related in this way. So in particular, A and A hat are related up to conjugation. So the way to think about this, conceptually, is that my LDS is this black box where I see inputs and outputs. And at the end of the day, this change of basis right here, applying this transformation U, is really just a reparameterization of the hidden state. So as long as I rename the hidden states inside my black box in the right way, I'm not actually going to change the input-output functionality of my LDS. And that's what this proposition captures, is this is the right way to measure closeness. So for our purposes, this tells us now how to define a very strong version of the problem of learning an LDS. What I want is that you give me a target accuracy epsilon, and I want a polynomial time and sample complexity algorithm that takes one long trajectory, and it outputs estimates A hat, B hat, C hat, and D hat that are close in the parameter distance I just defined. So that up to some unknown transformation U, everything is epsilon close in Frobenius norm. So this is the question I'll be interested in, and actually what's kind of fun is I'll be able to give you almost all the details of the key parts of the proof today, just in the next few minutes. So this is a very basic question, and what I'll be interested in is, exactly as I told you, whether there's a poly time and sample complexity algorithm. What's a bit surprising the first time you think about these learning things is that actually it turns out that even the sample complexity problem is really wide open for reasons I'll get into. So it wasn't even understood what are the information theoretic limits of learning from dynamics in this very simple context. So it's no exaggeration to say that there have been thousands of papers on the topics of learning linear dynamical systems. So there's no way that I can survey all of the papers that are out there. But I want to tell you about one assumption that occurs in essentially every paper, which is a very bad assumption. Now, it sounds like a benign assumption, but when you look under the hood and really think about it, you realize that it changes the nature of the problem in a pretty drastic sense. So what we can do is we can take our A matrix, remember that's the transition matrix. We can look at its spectral radius, which is the largest absolute value of any of its eigenvalues. And if the spectral radius is strictly less than 1, we say that the underlying LDS is strictly stable. If instead the spectral radius is less than or equal to 1, we say that the LDS is marginally stable. So at first glance, this looks like a very slight difference in assumptions, because it just differs in whether the inequality is strict or not. But what I want to convince you of is that there's really a world of difference between these two things. So first of all, what I claim is that strict stability fails in simple and very important cases. In fact, we've already seen examples where this condition fails. If you think about the example from the spacecraft motion, I told you that the transition matrix describes the laws of motion. So it's an upper triangular matrix of ones along the diagonal, and it definitely does not have eigenvalues that have absolute value less than 1. That's false. So it rules out some of the most important applications of control theory. Maybe more conceptually, what's really going on is that it precludes having long-range correlations. If I tell you the hidden state at some time step t, and I ask you what that tells me about the hidden state at some much later time, it tells me exponentially little. So basically, past information attenuates at an exponential rate because you're taking higher and higher powers of your transition matrix. So all the long-range correlations vanish. And relatedly, I set up my problem as trying to learn an LDS from one single long trajectory. But the truth is that when you have strict stability, in effect, you get as many trajectories as you want. You just take a short trajectory, you wait a long time until the system is mixed, and then you get a totally fresh sample that's virtually independent. In contrast, marginal stability is a much tamer assumption, is because if you don't have marginal stability, your system is exploding, because it's just exponentially increasing, and the problem really doesn't make sense. So I'll get more into details later, and what I'll leave as just a teaser for right now is that I claim that the problem is dead trivial when the underlying LDS is strictly stable. So that'll be a thread I'll have to close later. But for right now, what I want to assert is that in these thousands of papers, when you peer into the different theorems they all have bounds on their running time and sample complexity that have something like 1 over 1 minus rho of A. And that really just comes from assuming mixing in the underlying LDS. And they degrade very badly as the spectral radius approaches 1. So what I really care about in this talk is this more conceptual question, which is in the context of learning from dynamics. Is this necessary? Do long-range correlations fundamentally obstruct the possibility of learning? And I'm an algorithms person, so clearly the answer is yes, but there'll be some fun surprises along the way. So I told you what assumptions I don't like, namely strict stability. Let me tell you what assumptions I do like. There are actually some very natural assumptions that were studied back since the first papers in control theory. They were studied in an asymptotic sense, but these will really be the right assumptions, and we'll prove that they're essentially minimal assumptions. So this will be the other slide that I spend a little bit of time on, because this definition right here is really crucial to the talk. So I can define what's called the observability matrix of order S. So that's just a block matrix. Now remember, A is my transition matrix, and C is the matrix that describes the linear relationship between my hidden state and the observations. So I create this block matrix that looks like C, CA, CA squared, and so on. And what I claim, this is a very simple proposition, and I'll give you the sketch for it, is that if this observability matrix does not have full column rank, you're dead. And what I mean by that is that there are directions that you can move the hidden state in which you cannot see in the outputs. So this is really just a very simple, linear algebraic proof, right? So imagine that I give you the hidden state at some time step t. So I have xt, but imagine I move it in some direction z that's in the kernel of this observability matrix. Let's think about what happens when I take xt and add in this vector z to it. So I'm adding a perturbation. Well, by assumption, c times xt is the same thing as c times xt plus z, because z is in the kernel. And what that means is that there's no effect of this change on your immediate observation yt. That's what it literally means. And the same way, if I think about what effect it has on my next observation, yt plus 1, well, that's going to depend on c times a times xt. But again, z is in the kernel of c times at. So again, I have no effect on my next observation, yt plus 1, or any of the next s observations. So that's the proof of the proposition. It tells us that the full column rank of this matrix is essential, even if you aggregate information over consecutive time steps. If you don't have full column rank, you can't learn the underlying hidden state, and you can show that that obstructs learning. So it turns out there's a companion version to this that involves controllability and the B matrix instead, but it works in roughly the same way. I can define the controllability matrix. That's another block matrix. It looks like B, AB, A squared B. And what I claim is that if this matrix does not have full row rank, again, you're dead. And the point is that if it doesn't have full row rank, it means that there's some direction in the hidden state space that the control cannot push you in. Not immediately, not over the next step, and not over the next S steps. So in fact, this observation goes back to the founding of control theory, really, in the original papers of Kalman. The fact that if the infinite observability and controllability matrices don't have full column and row rank, then the problem is information theoretically impossible. And it turns out that those are the right assumptions actually for getting polynomial time guarantees too. You just have to make them quantitative. So instead of saying that my observability matrix has full column rank, I really need to assume some lower bound, a quantitative lower bound on its smallest singular value. So once I have bounds on the condition number of the observability and controllability matrices, then everything is possible. You can learn linear dynamical systems under marginal stability from one single long trajectory, and I'll give you almost all of the proof today. In fact, the running time and sample complexity of these algorithms, in case you're curious, it depends polynomially on the condition number. And even cooler, you can prove an almost converse to the statement that if for all orders S, your observability and controllability matrices are ill-conditioned, it's not the fault of your algorithm that it fails. The problem is actually information theoretically impossible. There's no way statistically to solve it. So these really are the right assumptions. Now, before I roll up my sleeves and tell you about some of the technical things, I want to take a step back and say some philosophical things. There is one paper I'm aware of that gave algorithms that works under marginal stability. This is a really nice paper of Simchowitz et al. However, it has a very important catch, which is that the running time and sample complexity have an unspecified dependence on the underlying LDS. In particular, they can be exponentially large, even in cases where that's not necessary, and polytime is possible. But I also want to take a step back and mention, these types of problems that I'm describing were studied in the first few decades of control theory, and then they were dormant for a period, and then all of a sudden there was renewed interest, no surprise, driven by deep learning. So it turns out that one of the things you can do is instead of looking at a linear dynamical system, you can add non-linearities after every step. That ends up being a very simple model for a powerful architecture in deep learning called a recurrent neural network. And when all of these things achieve amazing empirical success, people wanted to understand how does gradient descent work in fitting the parameters of these non-linear dynamical systems. The trouble is that there's no real way to build a general theory of that because of the non-linearity. A lot of these problems are computationally hard. So instead what people did was they revisited the old control theoretic ideas, and they used LDSs as a prototype for their analysis, as a building block for their intuition about what happens in the nonlinear case. So the whole time when they were proving things about gradient descent on linear dynamical systems, it was kind of like putting the cart before the horse, because we didn't actually understand what are the fundamental limits of the problem to begin with. We didn't understand things like why strict stability trivializes the problem. But that's a promise I owe you that I'll have to explain. All right, so I pontificated for enough, so let's do some theory. What I want to do first is I want to explain the blueprint. See, all these papers, the thousands of papers, were doing things on non-convex optimization, but I'm a simple guy and I'm going to try a much simpler approach, which is there's one blueprint that's been very powerful in theoretical machine learning. It actually goes back to the founding of statistics. One of the founders of statistics was Carl Pearson back in 1894. And he introduced Gaussian mixture models and the method of moments. And he wanted to actually fit these types of models to real data he had about the Naples crab. And he invented this very powerful paradigm that ended up being much more useful than what he originally imagined. So you have some unknown distribution that you'd like to learn. You know it lives in some nice class of distributions, but you don't know its parameters. So what you do is you take a bunch of samples from your distribution, and you use those empirical samples to estimate the unknown moments. And then you use those estimates of the moments to set up a system of equations that constrains your unknown parameters. And then you solve the system as a way to get provably good estimators. Now, Pearson's work was largely heuristic, but over the last 15 years, there's been a lot of work on giving rigorous guarantees. It connects to a lot of beautiful areas like, algebraic geometry, because a lot of times you end up with a system of polynomial equations. But in any case, this is really, one of the standard paradigms when you're talking about learning the parameters of a hidden Markov model, of mixtures of Gaussians, topic modeling, robust estimation. So what I'm going to do is, I'm just going to try and use the same recipe. Now, there's a big subtlety here, which, I shouldn't just try and brush under the carpet. See, in standard learning theory, the underlying distribution is stationary. There's one fixed mixture model, and you get a bunch of samples from it. In the context of an LDS, the trouble is I have one trajectory. And the underlying distribution, as I evolve time, is actually changing. It's never stabilizing. So really the question is there a way to make this recipe work even in the context of non-stationary data? So that's exactly what we're going to do. I'm going to show you that a very simple two-step procedure is going to work for learning linear dynamical systems. And it looks much the same way that the blueprint looks like in the rest of theoretical machine learning. I'm going to define some notion of the moments of my distribution, which are called the Markov parameters. This is another block matrix. It's got D and CB and CAB and so on. The way to think about this is that those parameters encode the input-output relationships in my LDS. But what I'm going to do is I'm just going to have a simple two-step procedure. I'm going to use my long trajectory to estimate the Markov parameters. And then I'm going to use the Markov parameters to come up with my estimates A hat, B hat, C hat, and D hat, and then I'll be done. In fact, even better, I claim that half of the work has already been done for me. It was done in the 60s, so that's good. We'll just have to solve step one. Let me explain step two so that I give you a full proof of these things. There's an old algorithm that goes back again to Kalman called the Ho-Kalman algorithm, which solves the second problem. If someone gives me the Markov parameters, what I claim is I can go to the estimates A hat, B hat, C hat, and D hat. So I'll prove that for you. And I should confess that when I tried to read the original paper, I got very confused. So what I'm going to do is I'm going to give you a different proof. It's probably the same proof, but my notation is better. So we'll do it this way. All right. So there's going to be a couple steps to this algorithm. This is the most opaque one, so just bear with me. What I'm going to do is someone hands me the Markov parameters, and I'm going to organize them into a Hankel matrix. You shouldn't see why I'm doing this, but you will on the next slide. So I create this block Hankel matrix. The top left corner is CB. The next anti-diagonal is CAB, and then CA squared B, and so on. And just as one more piece of notation, if I remove the last column in my block matrix, I'll call that matrix H1. If I remove the first column in my matrix, I'll call that H2. So let's try and demystify what I'm doing. See, someone gave me the Markov parameters, so I know this H matrix. It's just a matter of rearranging the things you gave me. But the key point, and I told you these observability and controllability matrices would come back, is that H is related to exactly those quantities. Remember, the observability matrix was this block matrix with C, CA, CA squared, and so on. My controllability matrix was B, and AB, and A squared B. So if you look at it algebraically, my Hankel matrix H is just the product of my observability and controllability matrices. So now you can start to see the hint of where the algorithm is going. Because I know the left-hand side, someone gave me the Markov parameters. And this hidden factorization that I wish I had is a thing I want to compute. That's what Ho-Kalman is going to do. But we can't compute this factorization exactly because it's not unique. Instead, we're going to compute it up to equivalence, the same equivalence that I gave you for the notion of what it means for two LDSs to be equivalent. So now the next step is really just to take the H matrix, which someone handed me, and compute any other factorization for it. and show that that factorization must be equivalent in the sense that I already defined to the unknown factorization that I wish I had. So let's think about this. This will all be simple linear algebra. Well, I can take this H1 matrix. Remember, I just removed that last block column. And I'll take the singular value decomposition of H1. So I write it as U times sigma times V transpose. U is orthogonal, V is orthogonal, sigma is rectangular with non-negative entries along the diagonal. That's not the product of two matrices, but I'll just split sigma up into two pieces so that I have two pieces of my factorization. And I'm going to suggestively call the first piece in my factorization O hat, because it's supposed to be an estimate of O, the observability matrix. And I'll call the second part Q hat, because it's supposed to be an estimate of Q. So what I should do next is I should relate this to the unknown O and Q matrices that I wish I had, right? And so remember that the same way H is the product of O times Q, H1 is too. You just have different subscripts because they go out to different orders. And what I claim is because O and Q have full column and row rank respectively, there's no choice. But these two factorizations have to be equivalent after an appropriate change of variables, after a linear transformation. So there is some unknown transformation T, so that O is equal to O hat after applying T, and similarly for Q, because otherwise I wouldn't have the right column space for my matrix. So this is just the basic fact in linear algebra, but now we're off to the races, and I can finish the proof of this old Ho-Kalman algorithm, which I still haven't read. The last thing I have to do is I have to estimate my transition matrix A, right? And now I should use H2 because I gave it a name. So remember, H2 is where I remove the first column. And when I remove the first column, I have at least one power of A at all times. So it's really not just O times Q, there's also an A sitting inside. So now I'm in good shape because I can use from step 2 the fact that O and O hat are related, and Q hat are related. And I know what O hat and Q hat are because they came from my SVD. So what I can do is I can left and right multiply by their pseudo-inverses to remove them. So when I left and right multiply by the pseudo-inverses of O hat and Q hat, then I'm going to get exactly A up to conjugation, the same conjugation, this unknown transformation T that described my uncertainty in O and Q. That's it. That's the proof. So that's good. We've covered this old paper from the 1960s. Actually, if you think about it, we need a bit more than that because in step 1, I haven't told you how I'm going to do it, but I'm going to try and estimate my Markov parameters from data. So there's no hope that I'm going to get the exactly right Markov parameters. What I really have to care about is also what's a stability analysis of the second part. Because invariably, someone's only going to give me the Markov parameters up to some sampling noise. This was done in a recent paper of Oymak and Oze. It's a nice paper, but it's also fairly intuitive, right? Because what's going on is that in the proof of Ho-Kalman, I just used the singular value decomposition. So you can use all of your favorite tools about perturbation bounds for the SVD. When is the SVD stable under a small amount of sampling noise? And everything works out, and you can dot the I's and cross the T's and get a bound in terms of what the stability is. So now we get to the heart of the problem, where I can actually tell you new things, and we can tie together a lot of the threads that I left open. So the main challenge is just step 1. I'm given one long trajectory. Where do I get these Markov parameters from? So what I'm going to do is I'm going to show you a very simple estimator that's going to sound like it solves the problem, but I'll be lying, so I want you to catch me. So what I claim first is that there's a very simple unbiased estimator for the Markov parameters. I told you the intuition for the Markov parameters is that they capture the input-output behavior of the system. That's literally true in terms of them being the covariance between an appropriately chosen input and output. So what I claim is if I look at the input, ut, and I look at the output at some later time, yt plus j, and I look at the covariance between the input and output, then as I change j, the time lag between the input and output, I sweep out all of the Markov parameters. So if this is true, there's only one way to prove it, which is just to check it, right? So let's check it in the j equals 1 case. The Markov parameter I'm supposed to get is c times b. And so I can take my first defining equation for the LDS. I can write yt plus 1 in terms of xt plus 1, ut plus 1, and this process noise zt plus 1. And I care about the covariance between yt plus 1 and ut, because that's the thing I want to understand the expectation of. I don't see any UTs here, so I can just unravel the recurrence. I can turn xt plus 1 into xt and ut. And now the important thing is that because ut is independent of all the other terms except for itself, it exactly picks out the CB term like I promised. So the proof for all the other terms is exactly the same way. You just unravel the recurrence. So now it sounds like we're done, right? Maybe I ended early. Because once you have an unbiased estimator in usual machine learning applications, you can just average it over a bunch of different time steps, right? So each one of these terms, yt plus j and ut transpose, is an unbiased estimator for one of the Markov parameters. And that's true independently of what t is. So why don't I just add them up and average them? That should be still an unbiased estimator for the Markov parameters, but I'm lying. There's a really critical assumption here, which is no one told you that this estimator, averaging them up, actually reduces the variance. So usually when you add up unbiased estimators and you average them, you're reducing the variance because they're independent. But here they're not independent. That's the entire point of the problem. And now I can make good on another promise which I made earlier on, which is that when you have strict stability, it trivializes the problem. So when people were studying gradient descent for linear dynamical systems as a metaphor for understanding recurrent neural networks, they were actually trivializing the problem. Why is that? Is because when I have strict stability, I do get independence as long as I wait long enough. So I don't average over every time step. I take an unbiased estimator at some time step. I wait a while. I take the next unbiased estimator at some distant time. And I keep averaging them up. And because the correlations decay exponentially, that's still good enough where I get a good estimator whose variance degrades. But let's aim higher, right? So what happens when we really do have long-range correlations? Is there an algorithm that tames them? So now what'll be fun is we're going to have to turn control theory on its head. Instead of control theory as a way to tame a linear dynamical system that I'm going to use control theory as a way to tame the variance of my estimator. So here's the key idea, and we're going to have to make this work over a couple of steps, right? Is that instead of using the original time series, y1 through yt, I'm going to engineer a new time series, y1 hat through yt hat. And I'm going to do that just by forming a new one in terms of linear combinations of the old terms in the previous time series. So somehow I magically want to choose these coefficients cj, so that first of all, I maintain the invariant, that it's still an unbiased estimator for my Markov parameters, because I have to solve step 1. But crucially, I want that this new change of variables, the transformation of my time series, tames the variance. So is there a way to choose the CJs in a way that these new y hat t's have bounded variance for all time? And let's do a first attempt, which isn't going to work, but it'll give us the right intuition for why this ought to be possible. So what I can do is I can take my transition matrix A, which I told you is the key to the problem, and I can look at its characteristic polynomial. And I can choose the CJs to be the coefficients in the characteristic polynomial. The important thing about it is just the Cayley-Hamilton theorem, which tells us that when I make that choice for the CJs, it's giving me a way to express a high power of A, namely a to the n, because it's an n by n matrix, as a linear combination of lower order powers of A. That's what it means, in the Cayley-Hamilton theorem. That's just the translation of the fact that you plug a matrix into its characteristic polynomial and you get 0. But for us, what's going to happen is that this expression right here is going to mean that we're going to create tons of cancellation, and we're going to cancel out all but some small number of transient terms. So the only way to prove this is to write down some horrible behemoth of an expression that I tried and I couldn't fit on the slide. So what I'm going to do instead is I'm just going to pretend my governing equations were simpler. I'm going to remove a bunch of the terms like the noise terms. You can just trust me that the cancellation works out the same way. I'm going to set the D matrix to 0. And I'm just going to have these two simple and governing equations. And let's check as a proof by picture that we get cancellation for all but the transient terms. So I take y hat t plus 1. that's defined in terms of the terms of my original time series for these coefficients that come from the characteristic polynomial. I can express, the yt's in terms of the xt's. I'm going to arrange things in a grid so that in a single row I collect together all the ut's and all the ut minus 1's and so on. And what I can do is I can take this xt plus 1 term and expand it into xt and ut. I'm collecting all the ut's in the top row. I'll expand these terms. I'll collect all the ut minus 1's together. I'll expand the next row. I'll collect all the ut minus 2's. And now you can see the pattern. See, if you think about this last row right here, what's going on is I have a power of a, namely a cubed, that I'm trying to cancel off with lower order powers of a. That's exactly what Cayley-Hamilton is designed to do. So even if I don't get cancellation in the first row because there's not enough terms to cancel, I eventually get cancellation once I go far enough down in this table. So if you work it out, what happens is you get this giant zeroing out of terms, and you have this y hat expression that only has some of the most recent ut's showing up. And the important thing here is that now the variance is not growing as a function of t, it's remaining bounded forever because I canceled out the long-range dynamics. So that's good. So I solved my second problem. Sounds like I'm almost done. I got a careful choice of the CJ so that I made the variance of my estimator be bounded independently of t. But remember, at the end of the day, I want it also to be a good estimator. I want it to have unbiased expectation for the Markov parameters. Now, I've actually messed that up because, if you take that expression from the previous slide, this is what I'd written down. This is what my y hat t is. And if I look at its covariance with some ut minus I, then the first term, that's c times a to the I minus b, is a Markov parameter. That's what I want. But there's this whole other mess after that that's messed up my expectation. So here it turns out that there's a very simple fix, which is instead of subtracting off the most recent terms, like yt minus 1 and yt minus 2, why don't I just wait a little bit? I'll wait r time steps before I actually start subtracting off terms. That has the advantage that ut minus 1 doesn't even show up there because it hasn't happened yet. So that way, my covariance between my y hat t and ut minus 1 has not changed because ut minus 1 hasn't even occurred. So this now solves the first problem too. You still get cancellation, but you do not change the expectation of your estimator. So I have a third attempt, which isn't obvious why I need a third attempt. I only had 2 problems, right? And it looks like I solved them. There's another problem which maybe you didn't anticipate, which is that I lied. See, no one told me that the coefficients of my characteristic polynomial are actually bounded in our polynomial size. That definitely does not happen in general. It need not be the case even for LDSs that I can learn. I'm just going to briefly sketch this. It turns out the right way to show existence of the CJs is really to appeal to condition number bounds and the observability and controllability matrices. See, when they're well conditioned, what it means is that when I add in another block in that matrix, the column rank is not growing, the row rank is not growing, so I can express that block as a bounded linear combination of the terms that came before it. But at the end of the day, what this tells us for the blueprint is really that there is a good choice for the CJs. So what I'm arguing is that if we knew the observability and controllability matrices, then we could argue the existence of a good choice of bounded CJs that have the right expectation, that have bounded variance. But at the end of the day, this actually sounds very circular, right? Because I got the CJs from looking at the O and Q matrices, and those are the things I wanted to begin with. So how do I break this cycle? And that's the last trick up my sleeve, which is that we can use convex programming. See, what I can do is I can write down a convex program that looks for a good choice of how to stabilize my estimator. I can search for a set of coefficients C1 through CS so that they're all bounded, so that when I apply those as my transformation of my time series, the new time series remains bounded. And then, a priori, I wouldn't know that this convex program is feasible, but what in effect I just did was I proved that it really is feasible. So the last thing you need to do to get the full algorithm is you have to argue that once you solve this convex program, it's not just that it has a good solution, given by the true CJs you're looking for, but moreover, every solution you find induces a good estimator. So what you can do here is, given some candidate C that defines a feasible solution to this convex program, I can define a potential function that captures the degree of cancellation. So, what's the variance of, the terms that haven't canceled out? And what you can argue through anti-concentration is that the only way that this convex program is feasible is if you really have a small potential variance that you've induced a good estimator that's bounded. All right, so that's mostly what I wanted to say about the technical content. I can't help but take a step back and try and philosophize a bit. I've spent a lot of my time, thinking about the method of moments. That's something that arises all the time in the context of theoretical machine learning. And, maybe it's not a surprise that the method of moments saved the day again, even in a different context, like learning linear dynamical systems. But in fact, I would argue that the thing that I described for you is really the beginning, not the end. Because what I could hope for more ambitiously is maybe there's a dictionary mapping the standard tools we have in theoretical machine learning to their dynamical counterparts. Maybe this isn't an accident that I had a variant of my blueprint that worked in the dynamical systems context. And maybe we can take our greatest hits in theoretical machine learning and ask if each of them has some manifestation when your underlying system is non-stationary. So let me give you a bit of a sketch about other directions that I think are really neat. Say, for example, there's a neat variant to this question you can ask, like what happens instead of having just one linear dynamical system with one long trajectory? What if at some unknown time it switches? It switches from system A to system B. This is the kind of thing we care about in the context of the spread of diseases. When we have different variants of COVID, they have different R naughts. So can we actually detect when exactly a system has switched from one to the other? It turns out that this is really a generalization of a very well-studied problem in statistics, which is called change point detection. There, what you have is you have a coin that starts off with bias P, and you keep flipping it. And at some point in the sequence of flips, the bias changes to Q. And what you'd like to do is you'd like to detect where that switch happens. It turns out that the right way to detect and get confidence intervals for where the switch happens is really building it on the problem of learning. When you can take a bunch of flips from an unknown bias coin and estimate the bias, that's exactly how you get confidence intervals for when the switch has occurred. So the same way, once you can learn an LDS, it should really be the starting point for things like, what's a dynamical version of change point detection, switching from one system to another. You could also ask questions about heterogeneity. In learning theory, we care a lot about, what if the underlying data isn't coming from just one source, but is a mixture of many different things? That was the question that Pearson originally sought to study back in 1894 with his Naples crabs. You can ask versions of this in LDSs. What happens instead of getting, trajectories from one single LDS? What if they come from all different kinds of heterogeneous sources and you don't know which one's which? In this case, you can hope that you can get algorithms that learn even in cases where it's impossible to cluster. So there's even more that I would want to say about other dynamical topics like reinforcement learning, like building algorithmic theories for modern RL, but maybe that's a topic for another time. So let me just briefly stop and summarize what I hope you got out of the talk. So I introduced linear dynamical systems, the two governing equations that are so powerful. I told you a little bit about why they have these wide-ranging applications across things like robotics, navigation, biology, epidemiology, medicine. And then I told you that about this pervasive gap in the literature, that algorithms that are out there all assume this nasty assumption called strict stability that essentially means you have no long-range dependencies in your time series. But it turned out that there was a very simple algorithm, once you articulated the question the right way, that actually can learn even in the face of long-range correlations. And more ambitiously, I hope this is the start of a bigger project on trying to understand algorithmic theories for control theory and RL much beyond these simple learning one system kind of settings. So I'll stop there, and we've got a few minutes for questions, but thanks for your attention.
Perfect. So we have a few of these microphones distributed, and feel free to come up and ask questions. We have close to 10 minutes.
Hi, just had a quick question. You mentioned very briefly that anti-concentration shows up. I'm wondering what results from anti-concentration you want to be using.
Great question. There's a little bit of a technical answer.
Sure.
But see, if you think about that convex program that I wrote down, what's happening is I'm looking for a choice of CJs so that they induce a new set of Y hats. And I want that for that choice of CJs, that the Y hats that they define remain bounded independently of time. Now, what I really care about is not whether, that's one sample, whether the choice of CJs stabilizes that particular realization of the underlying process, but I care about if I had those CJs and I reran the LDS, would it still remain bounded? So that's a different question, and I don't have a second trajectory to try it on. So what you have to argue about is that if the CJs didn't create enough cancellation, that there wouldn't be a way for them accidentally to define a new sequence Y hat that remains bounded forever. So basically what happens is that each one of these constraints, you have one for each different T, and you use a type of anti-concentration along those different constraints, coupled with some sort of net argument on the space of all CJs, as a way to argue that the only way that you pass this test is if you really have stabilized the variance.
So is there a paper where the particular anti-concentration results can be found? Or?
In the paper, I mean, we just proved what we needed.
Oh, okay.
Yeah.
Okay, because I'm aware of anti-concentration in a different context, so.
Yeah, so here it's not that we need any fancy anti-concentration tools, but they're really pretty ad hoc tools that still get the job done. But maybe one could get sharper balance, I don't know.
Okay, thank you very much.
Yeah.
I have a very minute question. So when you were formalizing the main problem that you were studying, I'm curious because you used the Frobenius norm. Is there any sort of connections you see to other problems or any ideas that you think you could find when you use a different matrix norm?
That's a great question. So in our context, it doesn't really matter that much whether it's Frobenius or spectral, because at the end of the day, what the running time and sample complexes are polynomial in n, which is the dimension of the problem, and 1 over epsilon, where epsilon is the target accuracy. So for our purposes, it sort of comes out in the wash in the sense that you can relate that and spectral up to losses in n, and it doesn't matter. But there are many other problems in theoretical machine learning where the choice of the norm is critical. So one of the things that I talked about very briefly was the method of moments is useful for robust statistics. So one of the questions I'd worked on a long time ago was the problem of robustly learning a single Gaussian in the presence of noise. And then you have the issue that I have some estimate sigma hat for the covariance, and the true covariance is sigma, and an adversary is corrupting epsilon of my data. So there the question is how do I measure the closeness? Is it in the spectral norm, the Frobenius norm? It turns out that the right norm is what's called the Mahalanobis distance. That looks like a ratio between the variances along different directions. And so those are cases where you don't want any extra losses in the dependence on n, and then it's really critical to have the right norm to measure it. But because here I was doing things more crudely with just polynomial time things, we don't see the difference here.
Thank you.
Thanks for a nice presentation. I'm wondering, for your proposed algorithm, actually, it has two kind of shaky parts for estimation. One, you need actually the SVD to be stable, and the other is you need to estimate the CJs. I'm wondering, do you have a sense of this algorithm is kind of minimax optimal in terms of estimation problem, or I understand that for theoretical kind of proof reasons, you need to do this and to do things very rigorously, or do you have any idea or whether there exists better algorithms that might have better statistical properties in this setting?
Very good question. So first, in the crude sense, when all I care about is the poly 1 over epsilon, all of the assumptions that you get in here are essentially optimal. So for example, what do I need in order to analyze the stability of my SVD? Well, I need the condition number of those O hat and Q hat matrices to be bounded. And so that ends up being exactly the same condition number bounds that you need in the other parts of the theorem and that you can prove are essentially optimal. So these things in control theory are called balanced realizations. So the O hat and Q hat you get from the SVD are actually the best conditioned factorization. But there's another question, which is a more fine-grained one, which might be the one you're also asking about, which is you can ask whether it's minimax optimal in terms of the dependence on epsilon, not in terms of the assumptions on the condition number. So there, the guarantees you get are actually 1 over epsilon to the 4th, and the optimal thing would be 1 over epsilon squared. It turns out the culprit is not the part that I gave you, but it's the Ho-Kalman algorithm. So the fact that you're sort of creating this like generalized eigenvalue type of problem is usually the thing that creates the wrong dependence on epsilon. And this is true even for simpler variants of learning linear dynamical systems. So there are problems called super resolution, where it basically corresponds to the diagonal version of learning in LDS. And in that case, people know better bounds in terms of the dependence on epsilon, but they crucially have to go through more direct convex programming approaches rather than some generalized eigenvalue problem.
Thank you.
Perfect. So we're just about out of time anyway. So it's a good timing to all the questions have been answered. With that said, Ankur will be in room 204 for the next short stretch of time, and you're welcome to go and discuss with him face to face and ask your burning questions that you didn't want to announce publicly. So with that, let's thank Ankur again for a great talk.